What is the microphone? চেক করে নিয়ে তো এখানে কোন টাইমটা কি সফটওয়্যার জার্মানি থেকে 18 সেপ্টেম্বর
Okay, so maybe let's start. So it's a pleasure to have Dr. Avijit Misra visit our group here in IMS. So Avijit, he did his PhD from HRI in Napa. Then after he did submitted his thesis in 15 and then our usual process took long time.
16.
16. Yeah. And then he was at postdoc here about 1.5 years ago. And then he went to this group of PhD in Weizmann Institute. So he has been there. So recently he got a postdoc offer from Howard Weizmann Group in University of Sydney in Australia. So he's waiting for the visa. So he's a faculty applicant. So yeah, hopefully he will start.
Good afternoon, everybody. Thanks for considering my application and giving me the opportunity to present my work. I'd like to thank Professor Ghosh for arranging the visit. So here is the plan of the talk. So I'll tell about my academic and research background, which is already mentioned by Professor Ghosh. And then I will discuss briefly about my primary research direction. And then before going to the work extraction by measurement and feed forward, I'll give a brief overview on quantum thermodynamics and work extraction. And then I'll discuss about work extraction by observation and feed forward, which is dubbed as OFF. And then I'll discuss about autonomous and over-dynamic work extraction, because in technological tasks, it is desired that the protocol is autonomous. So it's helpful if the protocol is autonomous. Then I will talk about ongoing works and near-term goals and future research plan. So Chivas already mentioned. So I did my BSc from Calcutta University in 2009, then joined HRI as an integrated PhD student and did my PhD under the supervision of Arun Kumarpati. And then I was a postdoc here. And then I joined with my Institute of Science in postdoc. Okay, and during my PhD and postdoctoral tenure, I have been teaching assistant to several courses like quantum thermodynamics and open system for graduate student, and also statistical mechanics and quantum information in action. Okay. So here is the primary research direction. So during my PhD, I have mostly worked on quantum resources like correlation, entanglement, and correlation beyond entanglement, and their interrelation with non-locality, and also characterization and quantification of quantum covariance and how to create covariance. And I have also worked on open quantum system, which is basically a spin bath system, and is strongly coupled to the environment and exhibit non-Markovian behavior. And it can be useful to preserve quantum resources in noisy scenario. And also I have explored the connection of information theory with thermodynamics and energy efficient quantum technology. Okay, so there I explore role of quantum resources in functioning of the machine. And presently I am working, or during my postdoc, I have mostly worked on quantum optics and hybrid quantum technologies, and also quantum sensing. So where major part of my study is based on atom-photon interaction in cavity. Okay, so it includes estimating dipole-dipole moment of the atoms in the cavity, and nonlinear noise sensing, optomechanical system, cross-cut nonlinearity, and also measurement-based protocols. And here, why hybrid quantum technologies are important? Because when you do quantum technology, some platforms are better for some specific tasks. Like suppose for operation of quantum gates and superconducting qubits are very good candidate, but due to low coherence time, if you want to store the information for longer time, spin system are better. And if you want to communicate some information, photonic system are the best. So the need of the hour is to work on the hybrid quantum system, where you can study several system and you apply the operation of superconducting qubit and store the information in spin system. So you can use the NV center system and also the this one cold system. But so these are like this overview of my work, which I'm. But today I will mainly focus on this part, like work extraction in optical setup. So using measurement-based techniques and cross-cut nonlinearity. Okay. So before going to that, I'd like to give a brief overview on quantum thermodynamics. So why we study quantum thermodynamics? Suppose we want to pull down a quantum system, say one atom, or we want to extract work from the atom. I'll mention in detail why this is important. So the question arises, to what extent the laws of classical thermodynamics hold in the quantum regime, where one cannot ignore the entanglement and coherence effect or the finite size effect. And it was a new field a few years ago also. And initially there were several claims. Then what can surpass the Carnot bound, like exploiting quantum resources, like entanglement or coherence. Okay, but if you scrutiny seriously, then you see that most of the claims arise due to use of non-thermal baths, for example, squeeze bath. So the Carnot theorem hold in the thermal bath, but if you use additional resources like squeeze bath, there's no wonder that you can go beyond the Carnot bound. Or the several claims are due to misleading or erroneous definition of heat and work. So let me explain a bit. Okay, so if I want to study the first law of quantum thermodynamics, so I start from a quantum state rho associated with the Hamiltonian H, and the average energy of the state is given by trace of rho H. And now delta change of the energy can be written as sum of these two terms. And the question was, and the study of quantum thermodynamics started by the work, seminal work of Alichki. They identified this as heat and this term, like change of Hamiltonian, as work. Just in similar fashion, like in classical thermodynamics, the change of energy of state is associated with the entropy change or heat exchange or work. But the question is, can we apply this division in quantum mechanical setup? Always. And the answer is no, we cannot do that. We can only use this when you are very close to the equilibrium situation. So if you are far from equilibrium, then there can be, this is not proper identification of heat and work. And so when we change the energy of the state, and suppose it is in contact with the heat bath and also there is a Hamiltonian driving, then how to differentiate between heat and work? So this was the important direction of study. And one intuitive reason that why this is not heat and work is that the change of state is not always associated with change of entropy of the state. So you can change the state without changing the entropy of the state. And that's why the error comes. The change here is not solely heat. So there it can be contribute to work also. Okay. And in this work, they have first studied and give a rigorous formulation that how much work we can extract from an individual quantum system which is in contact with the heat bath. So it is in contact with the heat bath, and the Hamiltonian of the bath is Hb, and say the Hamiltonian of the system is Hs. The pointer is not working. Okay, so okay, so here U is the global unitary that we operate on the system Also, there's a thermal bath. And the question is, our aim is to extract work. And in this kind of operation, which is equivalent to isothermal operation of classical thermodynamics, so how much work we can extract. And note here T is the temperature of the heat bath, because the quantum system might be in a state but temperature cannot be defined. So, and they have shown that the free energy E minus Ts, where S is the entropy of the state, can be identified as work done during this process. So, and they also established that this is the maximum amount of work one can extract. And if someone claims that they can extract more work than this, then there surely is a violation of the second law. And also they give a physical protocol how to extract work from an individual quantum system, which is in contact to a heat bath at temperature T and applying a global unitary. Okay, so this form is also people of stochastic thermodynamics, they use like free energy change as a quantifier of work during this isothermal operation. So in this direction, during my PhD, we have also worked on the Rayleigh entropic context, and there the equilibrium state is defined based on maximum entropy principle given by E.T. Jaynes in 1957. So he proposed that should be the equilibrium state. It should be least bad estimate given prior information. So I have prior information, for example, the thermal state, the average energy is fixed. So with this information, what is the most random state, or for which state I have less information? So, and thus you can quantify the equilibrium state, and we apply the theory in the Rayleigh entropic formulation. It's a entropy with the parameter alpha, and for alpha tends to 1, it corresponds to von Neumann entropy. And from this, we found the equilibrium state, and it can be shown the equilibrium state also minimize the free energy of the form F alpha equal to E alpha minus Ts alpha. And also, we have established that change in free energy is also the extractable work in isothermal condition. And this is consistent with the Carnot statement, and we have also established the Clausius inequality. And remember, we start from maximum entropy principle and then show that everything follows. And also in the identification of heat and work in quantum domain, the concept of passivity is also instrumental. So one can look into this paper for details, and I'll discuss about what is passivity. I'll discuss about it more when I present my work.
One comment about that distinguishing between work and heat and work.
Yes.
Right. So I mean, you said there's some issue of
yes. So you mean this formula?
Yes. So I mean, had this been resolved, like how to distinguish between heat and work in quantity?
Okay, so it depends on the context. If you are in equilibrium, you can use that. So now the other thing, like suppose you are in a isothermal condition and you are applying unitary. So this is the maximum amount of work you can extract. And they have given one protocol how to extract this maximum. But suppose you are working in a system or a situation, you cannot apply this unitary. Then you have to see that how much you can extract and what is the practical scenarios. And that's why the concept of passivity is important. And I will tell passivity tells how much you can extract from unitary. But again, it's a theoretical bound. Then you have to check in your context what you can do experimentally or what is the possibility. So I will discuss this in the course of my talk. Yeah, but one thing is like people agree that we cannot go beyond Carnot. So if we're in like using two thermal baths, it doesn't matter whether you use coherence. Okay. It's another direction I'll not talk about much. It's like also the people from information theory, they have rigorous formulation of thermodynamics law and its state transformation in quantum domain. And in this domain, one can also study like what is the cost of creating correlation. So suppose you want to create entanglement and your initial state is a thermal state. So how much energy you have to invest? And in this direction, we have also one important work, which is till date my most cited work. Like if you want to create coherence from thermal state and you want to create coherence in energy base. So what is the energy cost of that? And suppose you ask, like, you have limited energy. With limited energy, how much coherence you can create, and what is the best way? Okay. So initially the field was very much theoretical, but excitingly now it is very much also experimental, and people are doing several experiments, for example this. And I'm very glad to share that last week, or like 2 weeks back, there is a paper from India also, a group of people of ISC and JNCSR. They have studied the efficiency and power trade-off and beat that efficiency and power trade-off, and they have done a nice experiment. So this field is no longer of fundamental interest only, is very much practical nowadays. Okay. Now the question, like, why this like experiment on heat engine or work extraction or thermal management is important? Suppose you want to do a technological task, it might be computation or information processing. So you need to use quantum resources like coherence or entanglement. And the main challenge is to protect this from noise. Most of the time the noise is thermal. And so what you have to do, you have to insulate the system and cool down below a certain temperature. For example, in quantum computation, you need the qubit and you cool them by algorithmic cooling. So quantum refrigerator is very much important. And here I will. Okay, so no, the battery is okay because. Okay, so this is the simplest schematic of quantum refrigerator. So I have 3 qubit E1, E2, and E3 connected to 3 heat baths, TC, TR, and TH. And what is my aim? I want to cool the qubit which is added to TC. So TC is the lowest temperature here. And so the Hamiltonian is given. So when the particle, what is 1 is the excited state and 0 is the ground state. Okay. So what we want to do by what do we mean by cooling? So I want to transfer the population from the excited state to the ground state. So that is what I mean by cooling when I cool a qubit. So it is the aim here, and it is very much similar to the algorithmic cooling. Okay. So and now what you do, we introduce the interaction when the qubit, the population in the qubit say TC goes down in the ground state along with the population on the qubit E3 goes down, and at the expense, like at the same time, the population of the qubit E2 goes up. So what is the thing happening here? So when the qubit TC, say attached to TC, goes down, this means it releases heat, okay, and the heat is disposed to the another reservoir TR through the qubit E2, and for this we know that we are transferring heat from cold body to hot body, and for that we need some external work source or energy source. This is done by E3, and by this simply interaction, one can show at the steady state, one can have temperature TC S in the steady state, which is lower than the initial temperature. And this setup can be used to cool down the bath TC also. So this is one simple setup of absorption refrigerator. So here there are 3 qubits which interact, and the heat is deposited to the other qubit attached to TR, and we cool the qubit E1, and the work or energy for this refrigeration process is coming from the T. And later people have shown that only 2 qubit interaction is sufficient and replace third qubit by only a bath or noise source. So I have worked on this thing, and recently we have shown that we can have 2 qubit quantum absorption refrigerator with optomechanical, like 2-body refrigerator with optomechanical interaction, and we have used some parameters value which is people are using in the experimental labs. So we can test this theory in experiment in near future. Okay. So we have also studied the transient behavior of this refrigerator, and also what are the speed limit constraint on this refrigerator. Like I want to reach the steady state very quickly, so do I have to sacrifice the performance, coefficient of performance of the fridge? Okay. And another thing is, like suppose I cool down the system, and then I'm doing the information processing task or computation. During that, it can generate. Because like when you erase some information, there is heat generation. And what we need to bypass the heat. Otherwise, it will destroy the resource or it can damage the device. And for that, we need efficient heat management. And for this purpose, thermal diode and thermal transistor are very important. And I have also worked on this. And another thing is, it has been reported in 2020 that 11% of the global electricity is consumed by information and communication technology. So we want to always save energy, and presently the challenge or goal is not to make the quantum protocol efficient than the classical one, but also explore how energy efficient they are. So people are in this paper, you can see that people are also proposed figure of merit, which also include energy cost of this protocol. Say you are doing computation, it's not only takes like how much speed up it can do, but also like how much energy we need. So the goal is also do it in an energy efficient way. And in this situation, suppose we ask like for some information processing or computation, during computation, there is heat generation. So just simply dumping it into a bath, can we use the heat for work extraction, which can be saved as energy and can be used for future purpose?
I have a very nice question. So,
Yeah.
what is the scale of the generation? And when you're talking about damages to devices, I mean, is that in this scale comparable or?
Yes, it's comparable. So I'll talk about my work, and so I'm considering work extraction by photon detectors. So when you do these photon detectors, so the detectors got heated up, and you can calculate the energy. So it's like half Li square upon L is the inductance of the superconducting square, and I is the current. So current is of the order of 3 milliampere, and induction is around 500 nanohenry. And if you calculate, so you see this is a considerable amount with the energy required for some process. Okay, so thanks for the question. So I'll tell in detail. And also, like the heat is comparable, suppose, and so later, like suppose I'm detecting photons or something, and I keep the detectors or memory at some lower temperature. But absorbing the photon, it increase the temperature towards high value. And you need to pull down very fast for next cycle. And it's comparable with the energy that scale associated. And also one thing like the Landau eraser principle says like the energy is 50 ln2 to erase 1 bit of information. But to achieve this, you need very slow process. So when you do this erasing process in finite time, there is a trade-off how much energy you spend and how fast you do. And presently it's like a few thousand times higher than the theoretical model. And recently there are experiments where they're using quantum magnets to erase information, and they show that how we can reach the Landau limit. Okay. So now I'll go to, okay. So for work extraction, one method is to use measurement-based engine. So what is measurement-based engine? The idea dates back to Maxwell, where he proposed a thought experiment. Suppose I have ideal gas at some temperature say T, and the demon inserts a partition which has a window, and it controls the window. So it opens the window when the velocity of the molecules is higher than some certain value. Okay. And it closes the window when the velocity is lower than this value. And repeating this process, it can get the molecules which have higher velocity on the left side and molecules which have lower velocities on the right side. And thus, it can create a temperature difference. Okay. And in principle, it can use this temperature difference for extraction of work. But we start from a single temperature heat bath. So the demon can extract work from single temperature heat bath. And this was against the second law, because second law says you cannot extract work from a single heat bath. And this was the apparent violation of the second law. So why apparent? I'll come to that later. And this paradox lasted almost 100 years. And one idealized version of this Maxwell demon was given by Szilard. And Szilard considered one ideal hypothetical situation, like I have only one molecule. Okay, and the demon inserted partition just in the middle. Okay, and then demon measures whether the particle is the left or right side of this chamber. Okay, and if it notes that it is in the right side, it can attach a weight and just do isothermal expansion, basically doubling the volume, and get some work which is equivalent to KTLN2, that's doubling the volume. Okay, but one important thing is to extract the work, demon must need to know the position of the molecule, whether it is on the left side or right hand side. So it needs information, and here the information is 1 bit, because it's between 2 cases, whether it is the left or right. Okay, but the paradox lies there also. Like started, we are extracting work from single heat bath, and the paradox was resolved by Landauer, and where he proposed that there is a connection between information and thermodynamics. So when you want to release 1 bit of information, KTLN2 amount of heat is dissipated, and we need to invest the energy. And later it was generalized by Charles Bennett, but there are several criticisms on this Landauer principle, and it was said that it's hand waving to save the second law. There is no rigorous formulation, but now no one can complain that. There have been several works, but the most important work in direction in recent times is given by David Reeve and al. But they prove Landauer is a principle starting from minimum assumption. And what are the assumptions? Because the environment is in a thermal state, and from the beginning, the system and the environment is uncorrelated, and they apply a global unitary. And with this with this assumption, they have mathematically proved the Landauer eraser principle. Yes. No, but you cannot expect what then?
So let's say it's on the right side. Now it's literally on the right side.
Okay.
Then obviously one of them at least.
No, basically the thing is, what means you want to use this for purpose. So suppose you want to lift the weight, and that's why you have. It's not that you bring two weight and attach. So it can be other thing also.
No, I'm saying we were already attached.
Okay.
Now you said that you need to know the information about the location.
Okay.
Now let's say I don't know the location. It can be on right, it can be on left. But anywhere, wherever it moves, it at least leave one out.
No, but if you attach on the left side, so I got your point what you were saying, but here the task is like by expansion I'm extracting the work and I'm using this for the physical work. And here the work, like the load, suppose that my task is to attach a load, like lift a weight. So it's not that you put the two weight into both sides.
Take from like everywhere you like
Sorry. Can I repeat the question? I'll come to. Okay. So suppose the demon initially doesn't know whether the molecule is in the left or in the right. Okay. Now, so it has no memory, but the demon measures and it sees okay, it's in the left. So it has record somewhere. Okay. And then the left, when you want to write the memory, like do something, then you have to use the memory. So it's a physical system where it is encoded. like whether the measure and in the measuring apparatus or somewhere it is recorded that you get this value. And next time when you want to do, it has to be blank. So I'm going to discuss this more later on when in the context of photon detectors. Okay. So suppose the information can be gained by say counting for number of photons. So your detectors show some value, and then if you want to use the detectors, so you have to reset it. So here deleting it is reset. Okay, so it is known that if you have the memory at same temperature, you cannot extract work. But suppose somehow you can keep the memory at lower temperature, then in principle by this temperature difference, you can extract work. Okay, so here is one crucial point where our contribution comes. Note in Szilard engine or Maxwell-Raymond or any information engine proposed till date that we know of use an entire fraction for gathering information. So basically here they measure all the molecules, or here one molecule, so a fraction comparable to the input is measured. And you can have some I'll show later some engine where they are measuring only one photons, but still depending on the outcome, half of the times they waste the input. So here, so for measurement, interfraction is measured, and we asked the question: can you do it in a more efficient way? And our question was, we'll measure only a tiny part of the entire input and use this information to extract from the dominant unmeasured part. And we answer it affirmatively, yes, we can do that. And this is the setup. So what is the setup? So here I have a beam of light, but in principle, tools and techniques applied to atomic beam also. And here I have a beam splitter, which is high transmittivity. And most of the input signal passes through the beam splitter, and only tiny part is used for measurement. And depending on the measurement result, what I have to do, depending on the measurement result, I have to do some steps, like in Maxwell-Raymond or Szilard engine, to extract work. Okay. So all the rest of the talk on measurement-based work extraction is based on this concept. So if you have any question, feel free to ask. So here, and now we can say that what is the benefit of measuring the tiny part? Because it reduces the measurement cost and also the feed-forward cost. So you acquire less information, you have to erase less information, and the feed-forward cost, which is proportional to the information you get during the measurement. So it reduces the measure, but still we can extract work from the dominant unmeasured part. Okay, and what is the input here? So we do the calculation in coherent basis, and it applies to any mixture of coherent state, any classical mixture of coherent state, like probabilistic mixture. The P alpha is the probability distribution, and I show the result for thermal input. And a thermal state, you can the P distribution of thermal state is given. Okay, so the main crux of this part is like tiny part is measured, so we reduce the cost of measurement, and still we can extract work from the dominant part, and it results in higher efficiency. Okay, so when we
need to say that there is no trade-off between the information gained through measurement and the amount of work that
exactly there is trade-off, and that's why we have to do optimization. Like how much we use for information gain and how much is used for work extraction. So in this case, like if I have a thermal beam of photons, so this means suppose the input mean photon number is n bar, so it has been shown for optimal work extraction, square root of n bar photon is used for measurement. Okay, so you asked a question. Okay, so but before going to the work extraction, as I mentioned that it is very critical to define heat and work properly in quantum mechanics. So what do I mean by work in this context? Like how the work is quantified. Okay, so one definition is unambiguous in the sense, like suppose I have a quantum state rho and its energy is trace rho h. So I apply a unitary operation and lower its energy with respect to the same Hamiltonian h. Say for example, the Hamiltonian is constant. So what I'm doing, I have state and I'm reducing the energy. Can I do that? Yes, I can do. Suppose consider a qubit is in a pure state and I have the particle in the excited state. Okay, and the Hamiltonian is written, and then I apply a unitary and I bring it back, bring it to the ground state. So the difference of the excitation I can extract. Okay. And similarly, what I can do, suppose I have a two-level system in a mixed state, the mixture and the excited population is greater than the ground state population. And then I can again the same unitary and transfer it to a state, but the excited state population is lower than the ground state population. And then from these two, the final state, you cannot lower its energy by unitary operation. So when you cannot lower the energy of a quantum state by unitary operation, it is called passive. So what is the example? So suppose a system is in the ground state, the passive state. Suppose you have a D-level system and where the occupation probability decreases when you go in the energy eigenstate. And one example is thermal state. Okay, and why this is very useful way to quantify work? Because we are extracting energy by unitary operation. And when we do unitary operation, there is no entropy exchange. So the entire energy exchange can be considered as work. So this is the beauty of this definition, ergotropy. And from discrete variable system like qubit or D-level system, you got an idea what is the passive state. And the passive state, you cannot, as I said, that you cannot lower its energy by unitary. And so you can divide this energy of a state into some passive form or some ergot plus some ergotropy contribution. And for thermal state or any state which is not population invariant, the entire energy is passive energy. So okay, so it is about discrete system, but I'm working with continuous variable. So what is the scenario in continuous variable? Okay, see. So in continuous variables, the thermal state looks like that in phase-phase distribution. So if I see in the phase-phase distribution, a passive state falls off monotonically and isotropically, and it is situated at the origin of the phase space. Okay, now if I transfer the state from this origin to other locations, so displaced, it stores some ergotropy. Or I can squeeze the state. Again, it stores some ergotropy. Or it can be both, like both displaced and squeezed. Or instead of monotonic falling, there is this, here is a hollow crater in this distribution. So it is also non-passive. Okay, and non-passive means it is work source. We can extract work by unitary operation. Okay, and in my protocol, I said that I start from a thermal state. Okay, and it is a passive. So how can I extract work? When you do measurement or measurement on some parts on a passive state, it can render the state non-passive. And then it becomes a source of energy and we can extract work. Okay, so here the protocol, we start with a thermal state, which is passive, and we do measurement, which is homodyne here. And the homodyne estimates the phase. So when I have a beam of photons, so it estimates the quadrature x and p by homodyne detection. And due to detection in the tiny part, the dominant unmeasured part, it got displaced and also squeezed. And there can be some non-Gaussianity also. Okay, now from this, see, like if it is displaced or squeezed, I can bring it back to the origin by displacement operator and extract the difference of energy as work. So this is what we are doing in this step, work extraction state. And obviously the final state, which is passive, it's of lower energy from the initial state. And this energy difference is extracted at work. Okay, and this measurement scheme, you can think of classically. Suppose I have a pendulum and I want to use the potential energy of the pendulum. So for using the potential energy, we have to stop the pendulum when it's in full swing. If we stop it randomly, we can say that when it is at maximum velocity, but potential energy is 0. So for stopping it in the full swing, what we need to know? The velocity and the phase. Here, by phase estimation, we are getting the quadrature information on x and p and use this information to apply the operation like the displacement in the post-meta state. Okay. Okay, so there can be several operations, say squeezing or also non-Gaussian.
Start from thermal state.
Yes.
Then you apply the measurement to make it a non-vacuum state. Then you can expect more.
Yes.
One can ask the following question that is true for every measure. That how much energy you require to perform that measure?
Okay.
And how
so,
much work you can expect from the non-vacuum?
Okay, so here as I told that I can talk about detail tomorrow in the technical part. Like here we use photo detectors, right? So we consulted with the labs who are doing like photo detectors, single photon detectors, and there like the detection is it's a superconducting circuit and it's back the current. Okay, and there as I told the energy cost for measurement is like half L I square, and the value is L is 500 around a few hundred Henry, and this current is in milliampere hour. Now you calculate, and we have performed a study like how much mean photon number we need when you have this measurement cost, and like it is useful practically or just a theoretical step. So yes, so after few photon numbers, we can extract one. Now coming back to your previous question, like how much is used for measurement? Yeah.
Yes. So it's kind of set up. You explain like, would you say that measurement based engine or it is the information from the measurement that you are using? So it seems that measurement is costly. You are expecting one from measurement. All the information is given to the measurement that you are using to get extract.
I'm getting information from this. I'm using this information to extract what from the dominant part.
So how the information is playing the role? Let's take an example of the pendulum.
Okay.
How the pendulum's position is actually playing the role of our inspection.
Okay, so suppose you know the pendulum velocity and its phase at some time, and you want to stop it at some later time. Then you know if you know the initial phase at equal to 0 and its velocity, okay, or details, then you can stop. Otherwise, suppose at time t you randomly stop, cannot do. Okay. So here the quadrature information, what is the x and p rotation value, and you are using this information. Okay, suppose you do measurement and you don't record the x and p values, right? Then you don't know where you display state is and what operation you will do to bring it back to the origin.
But the system has already the potential to do that.
Yeah, obviously, like
the velocity has the potential already. Now you can extract.
Yeah, you have like if you consider say for example a thermal state. So you have let's say occultation probabilities. Okay, for example, say like two-level system. So your ground state population is more and excited population is less. But suppose you do a random measurement and it fits in the excited state.
Right.
And then from the excited state you can go to the ground state and extract the energy. But the thing is when you do like on average, what is the probability of getting in the excited state? So the average, on average, you cannot extract one.
I'm saying when after the measurement.
So what I'm saying that you ask like the measurement is disturbing the system and disturbing it from the passive to non-passive. So I say is this you can see from like a two-level system also. So QE is in a thermal distribution and you measure the, and it fits in the excited state. So you start from thermal state, but from measurement you go to a state of this first thing.
Yeah, I agree. I'm saying that when you go to the upper level, next after measurement, you got that the particle is in the excited.
Yes.
Now you just attach it with any automobile car, and it already has the potential to do that.
Yeah.
And you don't need to know that where the state, where the particle is, because of the act of the measurement, it is already polar excited.
No, that's so again it boils down to the question like what the whole way. So here I'm just tell me here, like you do the measurement and your state is displayed, but it's some state store energy that does not mean that you can use it unless you know how to extract the energy. So here for two level,
Or we that we don't know the quantum of energy that would be required. In the sense that, I mean, we have further weight, we don't store in, and we don't know the numbers and so on. But you can still extract the work if you want to. I mean, the quantum of energy that you need to bring it back to the state that that's right.
no, not the like how much you think how much energy I need. No, like what operation I will do. Like here, the display state, when I bring it back to the origin, like which displacement operator I will apply, that will depend on the makeup. So here, like if you don't know the information, there is no way you can. Otherwise, like
On an average, you cannot extract.
extract what on the average. So what you are saying, okay, suppose I see the excited states for a 2-qubit system, and I get the work, but on an average you cannot extract. And that is the thing, like okay, that you need to know the information. So if you do randomly, like suppose, for example, you see in the Zilliard engine, you randomly insert the partition. So it is either in the left or right. But if you don't know, like how you will expand.
Good actually. It will be, expression of the problem. He applies on the unitary.
Yes.
That also works. To extract one actually, you can apply different unitary operator and then you can see, and you can actually minimize and optimize it for maximum work you can. Yes. So I want to know that from this unitary protocol and measurement protocol, which one is advantageous and or is why?
So here, first, if you are asking in general or in this context,
According to
here the unitary is used for extracting work, and the measurement is to gain some information, and when you do the measurement, it is yeah.
It go away from the passive state, and then you know that.
Yeah. So for example, here, if you don't do measurement, there is no way you can extract work because you have a thermal state and it has like maximum entropy. And
Theoretically, we know that we can extract.
no, you cannot extract work from single heat bar. Suppose I give you a thermal state, that's the thing. Suppose I give you a thermal state and you apply unitary. So you can only increase its energy, you can increase, you cannot extract from it. So if you don't disturb the state from thermal, because it's the most entropic state given energy. So here, the measurement is required, and then from the unmeasured part, you are extracting the work by unitary. And why unitary protocol? For extracting work or by a paper entropy? As I said, that this is there is no debate like whether it is heat or what, because it is pure source of energy without involving any entropy exchange. Okay, now come to the question which is the ask, like how much we can use for measurement and work extraction. So here, the solid line represent the exact numerics, and when we have the photodetectors which detects photons, here, like the detectors absorb some photon and yeah, so the distribution is not Gaussian, for coherent state it is Poissonian. But if you work in the Gaussian approximation, and here P is the coherent state amplitude of the local oscillator. Okay, so we have to also optimize with respect to the local oscillator energy, not only how much we use for measurement, but in this case. Okay, so we optimize it with respect to the local oscillator energy and transmittivity, and it's shown that the optimized work is given by W max, and at the time we are not considering resetting cost or any other operation, we are only considering displacement. Okay, and it is shown that mean photon number greater than 1 is sufficient to extract work. And why mean photon number greater than 1? Why not greater than 0? Because you use square root of n energy for the local oscillator, and you use square root of n for measurement. So suppose you have 100 photons on average, you use 10 photons for getting information. And at the high temperature limit, so basically high temperature limit means when you have mean photon number higher, one can see this is the work division. So I will talk about details tomorrow. And here you can see that if I divide by the input energy, we can approach the efficiency 1 minus of the order of 1 over square root of bar n. Now by increasing the photon number, you can always approach, get closer and closer to unity. And that is the thing that we, the power of this protocol. Okay. And people can ask, okay, you are getting unit efficiency, whether it's violating thermodynamic law. No, we have performed analysis and we can discuss detail tomorrow. Okay. Okay, so this is the efficiency. And now you can ask that you are assuming your setup is all optical setup, and you are assuming that there is no noise. So what about noise? So we have considered every possible noise in the unused port of the beam splitter, and we have also considered the detectors are inefficient, and there can be dark counts. So sometimes there is no photons, but the detector shows some count. There is some photon. So this is called dark counts. So we considered all possible errors, and with this error, this blue line here represent the work extracted by displacement. Okay, by displacement when we don't consider the resetting cost, or when we don't consider noise. And see this below the blue dashed line, these detectors are 50% efficient. So even if the detectors are 50% efficient, as you were measuring on like a small part, what you can do, you can increase the photon number and you can always approach unity. And you,
Sorry, can you look at this schematic curves that you have and try to explain from there?
this one?
Yeah.
Okay.
Also, I mean, in terms of the noise, what is happening now?
Here?
So if you now have sources of noise, right? So it's like in that situation, so basically what is happening in the post-measure state?
Okay, so when you have this process thermal, take the expectation value of the quadrature x and p, it is a origin. Okay. So and also it is exposed from energy, but is in passive form. We cannot extract by unit. But by the beam splitter, when you measure on this part, it disturbs the state because this were correlated. So you measure in one part, and the other part, unmeasured part, was disturbed. If you don't do the measurement, then by the beam splitter, it's a passive operation. It does not change the p distribution of the input. So as you do the measurement, it changes it, and it renders the state non-passive. So it displays fluid, or it can be any other form. Okay. Obviously, it's lower energy from the input. Okay, and also some energy is used. Then you bring it back to some other noise of lower energy, and by this difference, you extract them. Okay, and I mentioned like
what are the sources of noise?
Yeah.
Oh, no, you are asking about the noise that is we are using for work extraction, or the optical noise that we have in the measurement.
I mean, both in principle, I mean, something in principle, I mean, optic and the instrument has some noise, and of course, in theory,
Yeah, so instrumental noise, the picture is second one, and here is the input signal, which can be a noisy light source. So this is my input signal, which is also noisy and passive because if you start from an active state or non-passive state, it's not useful. Okay. Then we consider noise like suppose the detectors is efficient, and suppose in the like this input noise we put deliberately put to extract work, but there are some spurious thermal noise in the unused port which you cannot control. So here, when you have noise, the efficiency decreases. But again, as all this noise is entering during this process, and we can extract work or we can get higher efficiency. And here the red dots, they are representing the eraser cost. And here we also consider, like suppose that we said that photon detector has some particular temperature, but if we are absorbing several photons, the temperature can increase. And you have to consider that also. Like when you're erasing, suppose for example, say just down some number, you start the photon detector at some temperature, say 1. arbitrarily. And then after absorbing the photon, it can go up to 5. Say. Then when you consider the resetting, you have to consider the detector temperature 5, not 1. So you have also accounted for. And here you see that with displacement we can get almost unit efficiency. So for high photon numbers, if we neglect the switching and other non-Gaussian operation, whatever it can be, so we don't need to bother about that. Okay, and we compare with other photonic Maxwell demon. Here the efficiency can be 1/3, so which is much less compared to our scheme. And also we compared with the finite time auto engine, and we have shown that is 4 times powerful than the auto engine. And you can ask like where the times comes in our setup. So basically the measurement are instantaneous, generally considered instantaneous. But when you reset the detectors, as I told that it is again of the order of thermalization time, because you have to do the resetting and the Landauer limit is an approach when you do in infinite time.
So here your photo detectors are single photon detectors or is what do we call this photon number resolving detector?
Okay, so here, what do you say, like, it's not single photon detectors, but photon number resolving detectors, but there can be such cases like, suppose the actual counts would be 5 and it counts less. So that's okay. And also, like, there can be error because the precision. So it's 5, it can also show 7.
Because you know, of course, one can design a photon number resolving detector to the type of form of detector.
Yeah. So actually, they are using single photon detectors. So they does not bother about like how many photons are there,
Right.
whether it's or no.
We still need to have photon number resolving detector. First of all, its efficiency is much less than the single photon.
Yeah.
And secondly, you know, there are further noises. You know, for example, you may have to reduce the temperature further to get the same efficiency instead of photon number single photon detectors compared to photon number resolving.
Yeah, because when you have more photons, the temperature is
that
higher.
is more energy.
Yeah. So in our next work, like theory, which I will be talking about tomorrow, and here I just mentioned, there we consider also this thing, like suppose the photon is we need to resolve one photon, like whether it is 5 or 6, and we don't have that precision. Say the precision is 5, so it cannot differentiate between 5 photons and 9 photons. So it's like it gives the count as 5, 10, and 50. So what happens in this situation? So obviously the efficiency reduces. And for analytic study, suppose you assume that in the photon detectors, like I have N1 and N2, and what is important, the difference between N1 and N2. And suppose I only get to know whether this difference is positive or negative. So I have 4 quadrants, and there I can do analytics, and the rest is numerical study. So in the analytics, so if we have this, so we have shown that the efficiency decreases. And like it's like very coarse grain. So you are using like so that the coarse grain thing after that. So in the extreme coarse grain, and I only know that which quadrant is positive or negative. So it is reduced by one factor of 1.25. Okay, so here the efficiency, what is the other temperature source? The other temperature source, actually how much? I have time, right? No, okay, but there is not question. Okay, then I will hurry. Here the detector temperature, like what you see, the detector temperature basically when you increase the mean number of photons, its the source temperature is much higher than the detector temperature. That's why you are not balancing carbon. The carbon efficiency also 1%. Okay, so I'll skip that because this is conceptually not new. So instead of photo detectors, if you put photo counts, what happens? So there we have a distribution like that, and we have to do computation in the fog basis to get work, and which is experimentally difficult. And we compare the efficiency, and homogeneity is better in terms of efficiency and experimental feasibility. Okay, so till now what we have learned, this measuring tiny part and use this information is advantageous, and homodynamic is better than photo count. But here we need a control step after the measurement outcome. So without that, we cannot do. So we ask, can we bypass this and can we do autonomously? So what is the question? Suppose I have a few hot beams and few cold beams, and I have an interferometer, and I let them interfere. And what is my goal? I want to concentrate the energy at some particular one pre-selected mode, say the topmost mode. And here the energy is concentrated not only in non-passive form, but it's also not in passive form, but non-passive form. So can we do it with linear interferometer? No. So with Bliss filter and phase filter, we cannot do that. We need some element which is non-linear. And what we have shown that here, that if we use cross-current interaction, which is Hamiltonian is given by this, or the chi is the nonlinear strength, and A dagger A and B dagger B is the number operator of the two modes. And what it does, it introduces a phase depending on the intensity of the input mode. And at the third stage, if I apply the cross-current interaction and then do one interference by pi/2 phase shifter and 50/50 beam splitter, so what we can see that we can get the energy from the output mode 4 in the mode 1, and also it's also in not in passive form, non-passive form. Okay. So this is the thing, and let us check like what is the efficiency of this thing. By optimizing the nonlinear strength, what we can do, we can concentrate 4/3 of the input energy of one mode, and C is the reflectivity, which is very much close to 1. So we get efficiency. So we start from 2 hot mode, 2 n bar is the input energy, and we concentrate in one mode on this form. Okay, so in terms of efficiency, is not as useful as this resonance scheme, but the main advantage is autonomous. You don't have to control. Okay, and what you can do, you can cascade it. So you feed the output of one input of the next one. So by cascading, you can increase this non-passivity and also store the energy. And if you want to see what is happening, so I think I'll skip. I'll talk about this tomorrow. Okay, so it can be there is experiment going on in Opus Fast-Sternberg lab at the Weizmann Institute, and they are introducing the nonlinear interaction. The photons are trapped in the Rydberg atom. Okay, the cold Rydberg atom, and what's been like what is the temperature of this Rydberg atom? They work in microkelvin. Okay, like 60 microkelvin, but there are labs which work on nanokelvin temperature, Rydberg atoms. So, and these photons are trapped in the Rydberg atom, and then there is dipole-dipole interaction between the Rydberg polaritons, and thus we can create the nonlinear interaction, and we are very hopeful that we will have the result very soon. Okay, so I have some future plan based on this nonlinear interaction, like study transistor, non-classical state preparation, or nonlinearity in noise sensing. Okay, these are some works I did in PhD, but I don't have time. I'll skip that. So this is some framework which I am building and which I will use for near-term research. So suppose I have a 2-level system which is coupled to a field mode in a cavity. And on top of that, the 2-level system, say, coupled to a bath at 0 temperature, and the bath is some special, like it has band gap structure. Okay, so if and the cavity and the atom is strongly coupled, like arbitrary coupling we are considering, the bath is weakly coupled. Okay, then you can see that a steady state, the cavity mode will be a exact Fock state for 0 temperature bath. Okay, and you can change the Fock state photon numbers by engineering the spectrum. Okay, and these are
because of engineering, because of you want to have the capacity of engineering the spectrum, you need this photonic band gap path.
Yeah, I need this photonic band gap paths material. There are photonic band gap materials, and then these are fields. Now we want to see the band gap and something that you can mediate by coupling the new field with the harmonic oscillator. And this is some techniques like there is one group who are working on like superconducting experiment or painter, they do this path engineering. And by this method, you can use like high photon number Fock state. And what is my future goal? Like suppose instead of one cavity, so I work on atom photon system. So I have one atom or multiple atoms interacting with multiple cavity. I have some recent papers on this in archive also. So if I have more than one cavity and the bath is non-zero temperature, can I create some unclassical state and which is robust against the noise because it's already coupled to the bath? Okay. So these are some questions I would like to work on in near future. Okay, and also I will study like what is the role of temperature dependent analysis, because when it's not finite temperature, zero temperature, there is a broadening of the clock speed. So how to control this? And here the bath we are using like perturbative master equation approach, but for practical purpose we want to study exact dynamics also. And we're trying to collaborate with Joachim Ankerholz's group. So we have a meeting. We had a meeting already. Okay. And another direction which I'm very much excited about recently, we have already writing one manuscript on this. Suppose in a cavity, I have few atoms, say 2 or 4 or 5. Okay. And the atoms are coupled to the cavity by coupling strength kappa A, kappa B, and so on. And the atom's dipole-dipole interaction is proportional to 1 by R cube. So it is 1 by R cube, not R cube. Okay. And so what is our goal? Suppose we want to measure the dipole-dipole interaction between the atom. And it is shown like when the coupling strength of the atoms with the cavity is equal or nearly equal, then some particular value of M, there is a crossing of the eigenvalues. And here the excitation number is fixed. Let's say, for example, we have one excitation cell between the cavity mode and the two atoms. Then if we see the eigenvalues, there are some particular M values where it crosses. Okay, so this is picture for two atoms and one cavity mode. And it is something like phase transition where you have eigenvalue crossing. And what we have checked, suppose we want to measure the dipole moment at this point, the Fisher information diverges. So here you can do the precise estimation of the dipole moment. Okay. And why it occurs, like at this crossing, what happens, there is a sudden population transfer from atom A to atom B. And due to this sharp transition, the Fisher information diverges. And we have like, we extend this for open and closed chain, and we consider like few atoms, say 5, 6, or 10. So in near future, our long-term goal is not to estimate the dipole moment only. Suppose there is a collection of atoms in a cavity, and it is very crucial to study the collective behavior when collective behavior of atom-photon interaction. It's very important platform for quantum technologies, and controlling the dipole-dipole interaction is crucial, because suppose you want to apply a gate based on two atomic state, then the fidelity of the gate will depend on the dipole-dipole interaction. So you need precise control of the dipole moment. And what we are trying to show, that when you limit the number of excitation, okay, and then you study the dynamics of a single atom, and by studying the dynamics or just measuring the excitation probability, okay, you can say that whether there is the dipole moment is randomly distributed or is uniform, or for example, whether there is a distribution of the coupling strength or is nearly equal, because it will exhibit through the dynamics of Fisher information. And also,
If particular atom we focus, is it arbitrary or it is also special?
okay, so this is some question which I was studying. Like suppose you start one atom from excited state, then you break the symmetry between the atoms. So this is, but suppose initially, like atom was in a ground state and cavity mode is excited by no photon. Then it doesn't matter which atom is measured, because it is like when it's uniform, so there is a delocalization. And now comes it was asked something like which were exploding. Suppose due to randomness, is whether there is localization of this exciter. So this can be randomness due to the coupling. So usually who studies this localization problem in many physics, I don't know this much. They use like the interaction between spins or the system. So here on top of that, you also have coupling with the cavity. And if the distribution, like dipole-dipole distribution or the interaction between the atoms, say it's a perfect delta function, there's no distribution, then if we randomize the coupling with the cavity, can we see something like localization effect? So this is some question we are trying to explore in near future. Okay.
And does it matter what geometry of atoms you are doing?
Yeah, it matters.
Geometry of cavity.
Right now, we have not explored or the geometry of the cavity, but the initial check shows the geometry of the atom atoms. Like here, you see the same parameter values, whether you have open chain or closed chain. So it's the crossing, the point of crossing is there. And that is the thing, because it is very sensitive. If you change the geometry, or if you change the coupling state, it's very sensitive. And that's why we're trying, like, we're checking for a few number of atoms, and it's so the drag pattern, and what we recognize the pattern. And it's like, it's not that we measure the distribution, but just measuring one distribution. Okay, we say, okay, there is a spread, or what is the mean of this dipole moment, or what is the spread. And whether with the finite accuracy or desired accuracy or not. So it's kind of like measuring one atom, it's like a goal. Okay. Okay, so this is my future research plan. It is the other plan. So there, when you study quantum thermodynamics or say some work extraction protocol, so there is gap between theoretical studies and experimental studies. So for example, you define ergotropy and you know, like you can lower its energy by unitary, but whether you can apply this unitary in lab or not. Like for example, after photocount, you have to do permutation in the fog basis, which is very difficult to realize in experiment. But displacement is easier. So I'm trying to explore like work extraction, work storing, and most energetic state in practical situation, and what is the scope of non-unitary operation, and what is the possibility of Gaussian operation, and what is the beyond Gaussian operation. And as I am studying like with one atom coupled to several cavity modes, the tools and techniques I used, the analytical tools and techniques, it's same when I work on optomechanical system. So I will try to explore how I can create robust non-classical state when the fields or say mechanical resonator or is coupled with optical cavity by some qubit, and I am controlling the state of the qubit, like for example. Okay. Okay, so the image like I saw here. So here I have an optical cavity mode and I have a mechanical resonator, and this is coupled to one qubit, and I'm doing measurement and I'm controlling the state of the qubit and what is the effect on these oscillators, and can I create non-classical state and whether they're robust or not. And also I will try to explore the link between quantum correlation and non-locality beyond 3-qubit system. And another direction is I want to study open quantum system where you cannot neglect the non-Markovian effect and how you can deal with the noise or strong coupling. Okay, and to design dynamical control to control the noise in this situation. And another direction I want to study like quantum sensing. So basically the sensing work I have done or I'm doing, it's in collaboration with experimental field where they are studying like it might be polariton and also NV centers, because I collaborate with Amit Finkler in Weizmann Institute for experiment related to NV centers. So I'm also interested in sensing mechanism based on NV center. they're good candidate for magnetization sensing and temperature sensing, because and also pressure sensing, because their ground state energy shifts in presence of temperature. And also in quantum sensing, I want to explore like how we can differentiate between non-Gaussian noise from Gaussian one, and by employing some nonlinear filter. Basically, the Gaussian noise is dominating, and we have also some non-Gaussianity in the noise. And if I need information on the non-Gaussian noise, I need to filter out the Gaussian noise. And also then gaining information on the non-Gaussian noise, how I can combat with the noise, or can we use it in the favor of the protocol. Okay. And also another direction is recovering lost information after decoherence. So suppose a state is decohered, but not completely decohered at some finite decay rate, and I do measurement at some multiple times, and then I can extrapolate to some extent in the Markovian regime, and fidelity will depend on the measurement time and how far you have started from the time t equal to 0. Then so for Markovian regime, you can get something which is not very difficult. Okay, it's challenging but not difficult. It's doable. But the main challenge comes when you have non-Markovinity in your noise model. Because of the ripples, you cannot do tomography at different time and extrapolate, because you don't know due to the ripples what to measure. So one thing is to apply some control technique, slow down the decay, and also reduce the ripples to apply the state reconstruction scheme. And we can also use some spectator qubits. Like suppose my system of study is say 5 or 6 qubit, I study 1 qubit, and to get some information on the noise model. And it's known that one can get the noise models are like path correlation time or the coupling strength by measuring 1 qubit, 1 or 2 measurements. Okay, and also check like whether the noise acts locally or globally. So this is something I want to explore. And also when I said that there are several works on Landauer principles, so like finite time is a finite time Landauer resetting. So there is plenty of scope working in this direction. Suppose if we have to dump the entropy from a memory, so usually we do in a thermal state. But suppose we don't have thermal state at our disposal, then what we can do? If I have a thermal state and I want to dump the entropy into that thermal state, so can we have some bound, some question like that? Or suppose I have finite particles into the bath to dump the entropy, and they are correlated, or they can be squeezed. Okay, and what is the implication of non-Markovinity in the resetting process? And also like what should be the dynamical protocol to realize the resetting process at some finite time but energy efficient. So these are some future direction. Thank you. So for your presence.
Do you consider work extraction for all the output values like take out and
When I calculate
like-
this,
yes, like
yeah, I do average. Like I can get several counts sometimes. So this is the average. So one time you can get
so someone
actually these are some details that we discussed tomorrow, but you cannot get. Yeah, there is only one point or one outcome you cannot get any more. When you estimate the quadrature, that is value x and p, like 0. So that's the photograph, and then the state is unknown at the origin. Except that point, the state is already displaced.
Yeah, but that is real.
Yeah, so it's like there's a 0 you can say. So I'll show that. Like, but this is rare when you increase the photon number.
Right.
Like when you suppose we check with
So
what.
does it mean that you bright light?
Yeah.
Yeah. So we need to do better result, or but you have to just control it. It's not the bright light, so it has more photon average.
Yeah. Yeah, so the more the photon number is, the more efficient it is. Yeah, and
For example, quantum battery purpose is measured in this method.
quantum battery,
Store energy,
like for storing energy.
storing.
Okay, so the in battery purpose you have some driving field you charge the battery. Basically, the measurement is like it's not immediate specificity, so it knows something.
For at least for that, we want to be.
Yeah. Basically, here also, like
When you want to extract work, then
in one case, like no, if I give you some system which is say not passive, then you can do unit check. It depends on the context. Here, what I mean, I'm disturbing the state, get away from the power to go away from the power. Like that you can do. Suppose you are thermal state at steady level system. Okay, say some high temperatures, you are getting suppose you are doing measurement and getting the higher excited state not normal, like not normal than the ground state, but from the lower temperature value. Then if you do measurement, suppose you get some excited state, and but still extra energy. The problem is when you do average and when you have to, the information you get, and when you have to erase the memory of the measurement device, you need to invest the same amount. Suppose you give the memory like at some lower temperature and you are measuring a thermal state, you can still extract work. So what you need to do measurement or whatever, you need to temperature.
that is the engine.
Not in the second law. Like whatever you do, you cannot.
Yes, we use the word you can.
Yeah, the exact law.
In the measurement of insanity, do you need photon number is only related or intensity detector suffice?
Okay, so what I have like I count the number of photons in one and n2. In one and n2, the spectrum is related to the expectation value of a.
So for that, because photon number is only detector, very less efficiency, and they do not even very high number of chemical one.
Okay, so you mean like you're saying higher photons, because
I am saying that if we have in the local oscillator if you have a strong laser,
Yeah.
then you can see the detector suffice. But in your case, will intensity detector suffice?
okay, so what do you mean by intensity detectors? Right? I count the number of photons because the intensity is given.
Yes. So intensity detector.
Okay, so I got like some number like if you have large photon, you talk about say intensity. So here, like our protocol is more efficient when you increase the mean photon number. And also, like if you are working with 10 to the 4 number of photons, so the local oscillator energy is comparable to the energy of 10 2 number of photons. But yeah, for lower photon number input signal, you need to increase the local oscillator energy very low. And there, what you were saying that how I can resolve the photon number. That's the problem. And that's why we do like force getting to the count. Like I need the count, like whether it is N1 or N2. And from the difference, I get the potential information. Error, like, these are the important numbers. That's why we can and talk about to there to reduce the exchange.
Last question, sorry.
No, it's okay.
In this one, you have considered single detector. This one for expected.
Work extraction,
In this case, you have considered
the measurement rate scheme.
single detector.
Here, I don't have basically reservoir.
You have already have thermal state.
I have thermal beam. Yeah, exactly. Highlight.
Somewhere it is already thermalized.
Yeah. Thermal. Okay, you can use this scheme for any noisy input. Also, passive.
So have you tried with two thermal like the usual scenario, right?
Two thermal.
Reservoir, two different temperature. And
Yeah,
you have
in a non-linear scheme. I have two hot mode and two cold mode.
Okay, okay, then you can extract even without measurement.
Yeah. So that was the like basic idea of this. You don't need to do measurement. And what you do, and you can call like
So you see
academic
some
model.
gain in energy,
Sorry,
gain in energy.
gain energy from the input.
Contact with extract energy like a heating.
No, here like the measurement is seen. What the concept of the cold bath found? Like what is the temperature of your detector? And another thing is when you dump the energy from which like the passive, that is like it's completely passive. When you have some source, some different temperature, obviously lower because you have reduced the energy. This is the source, but we don't use any heat bath. One heat bath is like your detectors.
Your system already, yeah, I mean, we have no separate paper. Your system is already thermalized.
Thermalized. Okay, and this like say optical mode. Thermal mode. Okay. So one mode state.
Thermal state.
And later what I have like two thermal mode. And the
Thermal.
and cold mode there it can be empty. Like that one, you can consider it as cold mode, or you can have less swing photon number. But here, so there also in the nonlinear thing, you have temperature difference. So it's like nowhere we're violating the thermodynamic law. Second law, or and also when we are asking like this nonlinear
Whether nonlinear
nonlinear helps, and you can call like not rigorous, just factually. It's kind of passive measurement because the one mode acquires the intensity, like acquires the phase depending on the intensity of the other. And we use this when you do the constructive interval. So it is like instead of doing measurement, you have two modes and you are estimating the intensity and storing this information in the phase, and then do constructive interference in particular mode reflected mode and destructive interference in what now.
Okay, good. If there is no more question, let us thank Avijit again.
And then they all will-
Over.
আমি এটা জানলাম ও আচ্ছা
যদি ভালো হতো পাচ্ছিল
অনেক
এই ছাত্রীদের সঙ্গে কিন্তু
তাহলে আমরা করে দেবো।
যেতে পারবে
তুমি কি
অসুবিধা নেই তো তাহলে আমি ওকে অ্যাপ্রিসিয়েট করি
স্যার এই মিটিংটা ক্লোজ করে দেবো।
পারবে এটা কোথায় পাবে
হ্যাঁ